Hey everyone, just going to go through the tension forces quiz I just gave you. I just want to make sure that we're all good, and there's some, I guess, misconceptions I want to go through with you as well right now. Okay, so we had the first question was this stationary textbook, and we're pushing down on the cover, and I was asking which of the following would be affected. So remember, if your book is stationary, what's happening initially is it's not really going anywhere, so the overall forces are zero, and you're going to have gravity and normal, right? Now, what changes is if you have an extra push downwards, that's going to be an applied force. So you're going to have an extra force going downwards. You still have the original gravity force. Remember, the textbook has not changed, so it still has the same force of gravity. That does not change. And because you have an extra applied force, the normal force is going to be bigger as well. So it's going to be larger by the amount that the F applied is. And the other thing, if you wanted to, you could be correct, is if you put down C. Even though the object's not moving, by pushing down, you make it harder to start moving. So the the static friction would increase as well. However, the coefficient would stay the same. The net force is still zero because you're not moving the textbook, and the acceleration is going to be zero. Hopefully that helps for that question. All right, next one. You got a student pulling a textbook across a desk at a constant speed, draw a free body diagram. Well, if it's a constant speed, alarm bells go off. Hey, there's no acceleration. And because there's no acceleration, that means that the sum of the forces must be zero in the x and in the y. So gravity, normal cancel. You're going to have applied, which is exactly going against the force of friction. So they kind of cancel in that way. Now, what did we do? What would happen if we put a second textbook on top of the original one? Well, what would happen is because we've got more mass, the force of gravity is going to increase. So it's going to go up. It should be Fg. It's going to go up, which results in a corresponding normal force increase. And the reason the force gravity increases is because you're going to have an extra gravity going downwards from the second book, not because the gravity is larger on one particular book. So I should clarify that. Now, because the normal force is larger, what's going to happen is this. In my equation, if you remember your friction equation for the force of friction, your friction is equal to the coefficient of friction times the normal force. So if the normal force goes up, your force of friction goes up. The thing to remember is the coefficient always stays the same. So I've got more friction, so it's going to double as well. The normal force is going to be larger, so you should make that larger. And the force of gravity larger again because you've got two textbooks worth of gravity over here. Now, what's happening is because I'm still pulling with the exact same force as before, my overall force is going to be backwards. We're going to accelerate backwards, and the book will eventually slow to a stop. So a lot of you didn't mention the slowing to a stop, or some of you forgot to increase the size of the arrows for the vertical components, the gravity and normal here. All right. Now, how did the addition of the second textbook affect the force of friction, the coefficient? Well, we talked about the coefficient. It stays the same. It's the same surface. The normal force is going up, so friction force is going up as well. We previously talked about that because they're directly proportional to each other. All right. Now, for the actual problem down here, problem solving, you have to remember when you've got these objects connected together, it's important to think of them as a system, but you have to tell people that it's a system. So since the toys are connected together, treat them as a system. You need to have some kind of statement at the beginning. And then you find your overall mass. So it'll be 1250 kilograms here. You tell me your system force. So here the force pulling the toys is going to be 1500 newtons of the three carts, right? And then you simply solve for your acceleration, and this is going to be the acceleration of each of the toys because they're all connected. They have identical acceleration. And because of that, I can now solve. So what we're going to do, we can solve again. Remember, two ways. We can go from car 1 over or go from car 3 and over. I'm going to start over here. So just like before, what happens is I'm going to draw my free body diagrams here. I know my acceleration is going to be 1.2 for all of these objects. Here I've got my tension 1 as well, but going backwards. Second tension force from the second rope. Here it is going backwards, exactly the same. And finally my overall applied or tension force at the beginning. Now, let's look at the first object here. So because I know the acceleration, and I know Ft1 is the only force acting on me, I can determine the Ft1 size by finding the net force. So we know the net force is equal to mass times acceleration. So we multiply the mass by the acceleration. So the mass of car 1, we get 300 newtons. That's my first tension force. So if I know this is positive 300, this tension force is going to be negative 300 on this object. That's, you're pulling, it pulls back on the other object. Third law. Then we've got the second object. The second object, what happens is we got the sum of the forces equal to Ft1 and Ft2 horizontally. Well, what do we know? We already know Ft1. We just figured it out over here. So it's negative 300. I'm going to get my acceleration from, and then we know it already, sorry. And we're going to figure out our net force. So it's the mass of car 2 times the acceleration, so it's 900. But remember, we also have the Ft1. So to bring it over, so the tension force here is going to be 1,200 newtons in the second cable. That means that the tension force on this side is going to be the same, but in the opposite direction, so negative 1,200. And then what you can do, if you really wanted to, you can just solve and double check to make sure your values are correct by doing an extra step here and solving for F applied, even though we already know, but you can just double check. So I won't go through that. So by going up to the step here, what we've done is we've determined Ft1, Ft2, that's all we need to do. So we just label them on my free body diagram up here, but just to clarify, this is what I'm looking for, okay? And that's about it. The only thing I might ask you on an assessment, maybe next year, would be this. What is the force of gravity and normal force for each of these? So you would have to add those into the vertical components. But for now, it's okay just to look at the horizontal component. So that's it. I hope you did well and you got some meaningful feedback from this video.